R is assumed to be a commutative ring with unity. It's got a 1, a unity, a multiplicative identity. A is an element of R. This notation looks a lot like what we've seen in group theory, right? Looks like the cyclic subgroup generated by A, but it's not. In ring theory, this is called the principal ideal generated by A, not the cyclic subgroup generated by A. Could it possibly equal the cyclic subgroup generated by A when you only consider the group operation of a ring, which is addition? Possibly. Sometimes yes, but sometimes no. As an example, in the ring Z, the integers, that forms a ring. It's an abelian group under addition, as we've always known here. It's also a ring. It's got a multiplication that's closed, associative, and distributive over addition. If you consider, for example, the cyclic subgroup generated by 2 in group theory, that would consist of all things you can obtain by adding 2 to itself over and over again. Also adding its additive inverse, -2, to itself over and over again. And it also includes 0. In other words, it's all even numbers. And that is indeed a subgroup of Z. How about if I think of it as the principal ideal generated by 2? I need to consider all ring multiples of A, in this case 2, as R varies over the entire ring. What do I get if I multiply 2 by an arbitrary integer? I still get an even number. Catching me? Catching what I'm saying here? I still get an even number. Therefore, the cyclic subgroup generated by A, where Z is an additive group under addition, and the principal ideal generated by A are the same thing for this example. But I will show you an example very shortly where it's not the same. Anyway, our goal is to show this is a two-sided ideal of R. We'll just say ideal of R, two-sided is in parentheses. We only consider two-sided ideals in this class. There are one-sided ideals in ring theory, but we're just going to often keep ourselves to commutative rings. And then one-sided ideals are actually the same as two-sided ideals. What do we try to show to prove this? You can use the ideal test. We've got a subgroup test. We've got a normal subgroup test. We've got a subring test. Now we have an ideal test. Ideals are the analogs of normal subgroups. Subrings are the analogs of subgroups. Ideals are the analogs of normal subgroups. Just like we use normal subgroups to make factor groups, so we will use ideals to make factor rings even today. So how do you do this? Use the ideal test. First, show it's non-empty. You got to show that this set is non-empty. What's an example of an element in it? A? Yeah, but according to the official definition here, it's technically only because R has a unity, so that you can take the R to be 1. A is in the principal ideal generated by A. Since A equals 1A, and 1 is an element of R, we were assuming the ring had a unity. So it's only because of that assumption that we can even guarantee that this thing is non-empty, at least according to this definition of this principal ideal. Then you want to show it's closed under subtraction. Really, that's like the one-step subgroup test. That's verifying it's closed under addition as well as additive inverses to show it's closed under subtraction. So if you've got two things, I'll call them B and C in the principal ideal generated by A, is there difference also in the principal ideal generated by A? What does this mean to be in there? It means you're of this form. There exists, say, an R1 and an R2 in R, such that B equals R1A and C equals R2A. We must show B minus C is also in this principal ideal. we have to show it has the right kind of form as R, a ring element, times A, the specific ring element. Just do what you would think you would do, make your substitution, and then factor out the A, which is allowable because that's part of the definition of a ring. Distributive property, essentially. Yes, with a minus sign instead of a plus, but remember, subtraction is the same as adding the additive inverse. So we really are using the definition of a ring there. That's something in R because R is a ring, so it's closed under subtraction. Therefore, this by definition is in the principal ideal generated by A. Then the last step is to do more than show it's closed under multiplication, which we needed to do with a subring test. It's more than that. We need to do show it's what I call super closed or super absorbent, you might say. It's like a paper towel that absorbs everything. Give me an arbitrary element of the ideal and an arbitrary element of the ring, and show that when you multiply those things, that you stay in the ideal. It's more than closed under multiplication. It's super closed. That's not an official term. It's just my own term. And here's the ring. Here's A. Maybe this is the principal ideal generated by A. It doesn't necessarily equal all of R. It doesn't in this case. But this is super closed. This example, multiply 2 by any integer, whether that integer is even or odd, you get an even integer. The result is still in the principal ideal. Give me an arbitrary little r in here. The product R times A and A times R, this is what makes it a two-sided ideal, must actually be in here. RA and AR in general must be in there, but we're only considering a commutative ring anyway, so RA equals AR. It's got to be inside of this principal ideal. It can't be outside of it. And that happens no matter what R is. Under products, these things are getting sucked in, so to speak. It's not as hard as it sounds to verify this. B being in the principal ideal generated by A means there exists a, I guess I'll call it on R1 in R such that B equals R1A. Now verify that R times B and B times R are in the principal ideal generated by A. That's easy. Substitute associative property. That's an element of R. This is therefore in the principal ideal. And B times R, well, I'm assuming the ring is commutative, is R times B, and so then we can just go and do the same steps, because I'm assuming the ring is commutative. Yeah, we often are going to assume rings are commutative for most of our examples and many of our theorems, because it just makes things simpler from here on out. Yes, there is a big theory of non-commutative rings, and matrix rings are an important example. But for the most part, even though it's not part of the definition of a ring, we will often assume our rings are commutative. Okay, so I'm just indicating use commutativity there to make it simpler. I mean, that's what you would have to do anyway. Therefore, this thing, this principal ideal generated by A, is in fact an ideal, as its name implies. It's an ideal of the ring R by the ideal test.